All right, let's talk about C. Today, we're going to get our hands dirty with one of its most defining, and let's be honest, infamous, features, manual memory management. It's the very thing that gives C its incredible speed and power, but it's also a total minefield for bugs. So let's break down exactly how it all works.
So, here's the game plan. We'll kick things off with why C's approach is such a superpower. Then we'll explore the two main areas where memory lives, the stack and the heap. From there, we'll dive into the dangers of pointers, look at the most common ways things go wrong, and finally, wrap up with how you can actually tame this memory beast.
So first up, what exactly is this memory superpower we're talking about? Let's take a closer look at what makes C's direct line to memory so special and frankly so fundamental to just about everything in computing.
And this quote right here, it just hits the nail on the head. See, unlike a lot of modern languages that are constantly holding your hand and managing memory for you, C just gives you the keys. It gives you that fine-grained control over the hardware resources. And that isn't just a feature, it's the entire philosophy of the language.
And why does that matter? Well, this level of control is exactly why C is the bedrock for so much of the critical technology we use every single day. We're talking about the operating system on your computer, the tiny chip in your smart home device. For these things, performance and direct hardware access are absolutely non-negotiable. Okay, so when you run a C program, where does all your data actually go? This brings us to the two main regions of memory every C programmer needs to know, the stack and the heap.
The best way to think about this is with a simple analogy. The stack is like a stack of plates at a cafeteria. It's super fast. The last plate you put on is the first one you take off. It just manages itself. The heap, on the other hand, is completely different. Think of it like a massive valet parking lot. You have to specifically ask for a spot, you get a ticket, which is kind of like a pointer, and you absolutely have to remember to tell the valet when you're done so they can free up that space.
This really highlights a key difference. You see, most variables that you declare inside a function, they're temporary. They live on the stack, and they just vanish the second that function is finished. But if you declare a variable as static, it's a whole different story. It gets its own permanent spot in memory and sticks around for the entire life of your program.
So what's the big takeaway here? It's all about a trade-off. The stack is automatic, it's incredibly fast, but it's small. If you try to push too much onto it, you get a stack overflow. The heap, though, is huge and flexible, but it's slower, and it puts all, and I mean all, the responsibility on you, the programmer, to manage it correctly. And this whole process of manually managing the heap, it has a name: dynamic memory allocation. You do it with just a few key functions. Malloc is for grabbing a chunk of raw memory, calloc does the same but also clears it to 0 for you, and free, well, free is the one you must call to give that memory back.
Okay, so how do we actually manage all this memory on the heap? The answer is pointers, but as we're about to see, they are a true double-edged sword.
At its core, a pointer is actually pretty simple. It doesn't hold data itself, it just holds the address of where the real data lives in memory. It's literally that valet ticket we were talking about before.
But what happens when you use that ticket wrong? What if you try to go to a parking spot that doesn't exist or one you don't have permission for? Well, the operating system steps in and it's not very friendly about it. Now, this right here is a perfect example of how simple the mistake can be. We create a pointer, p, and we set it to null, which basically means it's pointing at nothing. Then, on the very next line, we try to dereference it. We try to go to that nothing address and stick the number 10 there. And bam! Segmentation fault. This is the operating system's way of slamming the door in your program's face. It just says access denied and shuts your program down immediately to stop it from corrupting anything else. It is, without a doubt, the most infamous crash in C programming.
A seg fault is just one of the many ways things can go sideways. So let's move on and take a quick tour through a catalog of other common memory catastrophes.
First up, the dreaded memory leak. This happens when you call malloc, but you just forget to call free. The program loses its ticket to that piece of memory, so it can't use it or give it back. For a long-running program, like a server, this is basically death by 1,000 cuts.
Now, the flip side of that problem is the dangling pointer. This is where you do free the memory, but you keep trying to use the pointer that used to point to it. The problem is, that memory could now be used by something totally different, leading to unpredictable crashes, data corruption, or even major security holes.
And then there's the big one, the notorious buffer overflow. C just doesn't automatically check if you're writing past the end of an array. If you do, you can end up overwriting other variables, crucial program instructions, pretty much anything. This is one of the most classic and dangerous security exploits in computing history.
And this makes the solution crystal clear. Old C functions like gets and stroppy, they just copy data and don't care how big the destination is. The modern, safer versions like fgets and string fgets, they force you to add one extra piece of information, the maximum size to copy. This one little change prevents the overflow before it can ever happen.
Now, I know this all sounds pretty scary, but it's not a lost cause. In our final section, let's go over the core principles you need to follow to tame the memory beast. The rules for staying safe are actually pretty straightforward. Number 1, for every single malloc, make sure there's a matching free. 2, always check if a pointer is null before you try to use it. 3, to avoid those dangling pointers, set the pointer to null right after you free the memory. And finally, always choose functions that let you specify buffer sizes.
And just when you think you've got it all figured out, C has one last little surprise for you: structure padding. To make your code run faster, the compiler can actually sneak invisible padding bytes into your data structures. The key takeaway here is that the size of something in memory isn't always what you think it is, which is just another reason to be extra careful. So if you remember just one thing, let it be this: C doesn't hide memory from you. It gives you direct, raw, unfiltered access. That's where all its performance comes from, but it demands discipline. It's not just programming, it's having a direct conversation with the machine itself, with all the power and all the responsibility that comes with it.
Which really leaves us with a final thought to chew on. Modern languages, with their automatic memory management, have definitely prevented countless bugs, no question. But by hiding all these details away from us, are we maybe losing a fundamental understanding of how our software really works with the hardware it runs on? Something to think about.